Okay, and I think we can start. So welcome everyone back, and to the sales workshop, to the second session of the sales workshop from today. So that means Manish Kushwaha and Thomas Nowak, we are very happy to have you here. And of course, we are very excited to have Kurt here, who was so nice to give a talk here. And just a very brief introduction. So Kurt is Director Emeritus at the Max Planck Institute of Computer Science in Saarbrücken, and he's Senior Professor at the Saarland University. He's very well known for many papers on algorithms and their complexities from a very broad range of perspectives. And he has authored several books, hundreds of papers, and received several awards. And we are very happy to have him here today.
Matthias, thank you very much for the introduction. Can you all hear me? We have solved the first problem. So this is joint work with quite a number of people. I started this work 8 years ago, with Vincenzo Bonifaci together. The other co-authors are Enrico Facca from in Pisa, from the École Normale in Pisa, Frederick Foltz and Giovanna Morigi. They are both in the physics department here in Saarland University. Andreas Karrenbauer is one of my postdocs. Golnoush and Quentin Golnoush is my PhD student, and Quentin was a visitor from École Normale in Paris. You can find the paper on arXiv. So what is the paper about? So what is this Physarum? About 10 years ago, I watched one of these science magazines on TV, and they reported about an experiment with a slime mold. So this is the stuff that grows in your refrigerator if you're not careful. And so this slime can form cells the size of a hand, and you can treat the slime absolutely gruelly. You can cut it into pieces, and then are big cells with many nuclei. So you can cut it into pieces, and then if you put these pieces next to each other, they unite again. And so the experiment they reported about is the following. They built a maze as shown on the left and covered it with slime. The yellow stuff is the slime. How did they build the experiment? Very simply. They took one of these old-fashioned overhead foils, so a plastic foil, and they cut out the maze. These plastic foils are very dry, and the slime doesn't want to live on a dry surface. So it only lived in the gaps between the foil, and this is what you see in yellow. Then food was provided at 2 places in the form of oatmeal, and then the slime retracted in half a day to the shortest path connecting the 2 food sources. This is a paper which appeared in Nature in the year 2000, and in the paper they write that they tried this with 20 different mazes, and in each case the slime found the shortest path. So when I saw this, I was intrigued, but I was also offended because one of my most cited papers is about shortest path, and here is the slime. It doesn't even have a brain, and it can also do it. They got for this work the Ig Nobel Prize for achievements that first make people laugh and then make them think. This is exactly what happened to me. So I saw this on TV in 2012. The next morning, I read my daily newspaper, and on the science page, they also reported about this experiment, and they gave references. So when I came to the university, I went to the library and looked at these references, and then I told Vincenzo over lunch, and we sort of said, we have to find out how this works. How does the slime do it? And here is the outline of the talk. I already reported about the amazing. Oh, by the way, you can interrupt me at any time. Yeah, just I guess just shout. Turn on your microphone and shout. Then I will talk about the mathematical model for the dynamics of the Physarum. I will go back to high school physics and do a short review of electrical flows. Then I review our result from 2012 on shortest path. And then in the main part of the talk, I talk about network formation. I first show you the wet lab experiment. Then a Physarum inspired mathematical model. I already say now that we do not claim any biological relevance. I tell you about experiments and about theory. I mean, what we can prove about the dynamics and how the dynamic performs on toy examples. So there is a paper that appeared in the Journal of Theoretical Biology in 2007, where a mathematical model was introduced for the maze experiment. And the author said Physarum is a network of tubes. The flow through these tubes is determined by concentration difference at the endpoints of the tube, the length of the tube, the diameter of the tube. These tubes adapt to the flow through them. If a lot of material is pushed through a tube, a lot of material relative to the diameter of the tube will grow. If very little flows through a tube will shrink. And so they discuss this in the first half of the paper, then they develop the mathematics in terms of fluid flows and hydraulic pressure. And then they say, okay, let's look at these equations. It's the same as flows in an electrical network with time-dependent resistors. And most people are more familiar with electrical currents than with hydraulic flows. So they wrote down the model in terms of electric currents. And I show you their model on the next slide. So they said, we have an undirected graph, two special nodes, S0 and S1. These are the food sources. Each edge in this graph has a length, which is a fixed number, and a diameter or capacity, which I denote by x sub e of t. And this is a dynamic quantity. It changes over time. Initially, all these capacities are positive, and I use x sub t, so without a subscript, denote the vector of all these diameters, of all these capacities. And then we send 1 unit of flow between source and sink. And we're in an electrical network where the resistance of an edge equals to length or cost divided by capacity. Or another way, the conductance is capacity divided by cost. If you have such an electrical network, you will have a flow through every edge determined by Kirchhoff's law and Ohm's law. And let me denote by Q sub E of t the resulting flow across E at time t. And then they postulated this dynamics, namely that the derivative of the capacity of any edge with respect to time is equal to the difference between the flow and the current capacity. And the flow is in absolute values because it doesn't matter whether it flows in this direction or in this direction. And so if the flow is larger than the current capacity will grow. If the flow is smaller, the capacity will shrink. This is the model which they postulated. And then they also report about computer experiments that indeed in this model, the capacities always grow to, or the capacities always find the shortest path in the following sense, that the x values for the edges on the shortest path converge to 1, and the edge values for edges not on the shortest path go to 0 as time goes to infinity. This is what they observed in computer experiments. Now let me briefly review electrical networks. So this is high school physics. We have again this undirected graph. We have these two special nodes. We send 1 unit of current between the two nodes, and the resistance is R over C over X. And let me use A for the node arc incident matrix of an oriented version of G. So this is a matrix which has one column for each edge. And for an edge, there is a +1 and a -1 at the two nodes incident to the edge. It doesn't matter which endpoint you denote as plus and which as minus, just that you orient the edges somehow. And all the other entries in this row, in this column, are 0. Then we all know that electrical flows are driven by node potentials. So that means for an edge UV, the flow across the edge is equal to the conductance of the edge times the potential difference. So this is PV minus PU. And in matrix form, you can write this as X sub E divided by, so the conductance times the east column of this matrix times the vector of potentials. And if you want to write everything, you can write it like this, where the X and the C are diagonal matrices with the entries are the X values and the C values. So this is just Ohm's law. And then there is also flow conservation. And flow conservation you can write in matrix form as if you take the vector of flows and you multiply it with the A, then you see the net flow at each edge, and this is plus and minus 1 at the source and the sink, and it's 0 otherwise. If you put this equation and this equation together, then you get an equation for P, which reads like this, where this matrix L is this here times A. It's not important what the exact formulas are. The only thing I want to remember that it's fairly simple and that one can compute the P and the Q by solving a linear system. This I will need more often. Electrical flows dissipate energy. So if Q is the electrical flow, the dissipated energy can be computed in many different ways. So there is a local view and a global view. The local view says sum over all edges, the flow across the edge times the potential difference, and sum up over all edges. This you can also write as R sub B Q sub B squared. The global view says look at the potential difference between source and sink, and this is also the dissipated energy. Remember that we are sending 1 unit of flow. Yeah, so the potential difference between source and sink, this is also the dissipated energy, and this is sort of a local view, and this is a global view on dissipated energy. And because B is defined like this, you can also write the dissipated energy like this. Any questions at this point? So in 2012, Vincenzo, Girish Varma, and I, we proved that this is not a coincidence, that the computer simulations converge to the shortest path, because we proved that for any graph, it is true that if you let t go to infinity, then these capacities go to 1 for edges on the shortest path, and they go to 0 otherwise. Also, the dissipated energy converges to the length of the shortest path. So dissipated energy is this, I had it in the previous slide. The length of the shortest path is this, because remember the x converges to a 0, 1 value and has only 1 for the edges on the shortest path. And also the potential drop on an edge converges to exactly the cost of the edge for edges on the shortest path, and for something less, which is for edges which are not on the shortest path. The way I phrased this is assumes that the shortest sourcing paths are unique. There is a similar theorem covering the general case, but it's more complicated to state, and I state is the simplest case here. Yeah, let me show also a visualization. The image here was produced by Vincenzo. So let's say we look at this very simple case. We have the source and the sink and 2 parallel edges, and the one on the top is shorter than the one on the bottom. And these edges have a certain diameter, x1 and x2. And then let's look what I have here on the right side. So I'm in the x1, x2 plane. And what I depicted for each point, x1, x2 in the, I showed the vector x1 dot, x2 dot, which is computed as flow minus current value. And then these derivatives give rise to trajectories by just following these arrows. For example, if you start here, the dynamics is like this, and it will converge to a point where x1 is equal to 1 and x2 is equal to 0. Similarly, if you go in like this, and so on. Okay, so this is a visualization of the dynamics for the simplest case. Now, here is the network design. Now we come to the main part of the paper. So this is a paper which partly by the same authors, which appeared in Science 2010. And they performed the following experiment, among others. But so they said, the slime is not allowed to grow outside this region here. And for some of you, this picture might look familiar. Is there any Japanese in the audience? So if you look at the map, this is sort of an outline of the greater Tokyo region. This is Tokyo Bay. And this is Tokyo. And then they provided now not food at one place, but at many places. All the yellow dots are food. So little pieces of oatmeal. And then they put the slime in the middle, just on the big dot here. And then the slime grew outwards. And after, again, a few hours, it formed this network. Yeah, so it first it grows outwards and covers the surface almost uniformly, and then it shrinks down to a network. And then it's a short paper, 3-4 pages. And then they compare it to minimum spanning trees and the network consisting of shortest path. And they also do computer simulations. And the punchline of the paper is, this is the last paragraph of the paper, that they put down a picture of the railroad network near Tokyo and say, and our railroad engineers are outstanding, Japanese railroad engineers are outstanding. And next to it, they put the network built by the slime. And then the last sentence is, aren't these networks surprisingly similar? Yeah, that's the punchline of the paper. And again, already in 2012, we asked ourselves, how can this happen? And yeah, and we worked on this on and off. I mean, we finally wrote a paper a few months ago, and actually a quarter page of what we wrote in 2012 is still in the current paper, but only a quarter page. And so I want to go into this now. So we modified the model. So we treat a network design problem. As before, we have this undirected graph. We have a positive cost function on the edges. But now we do not have a single source sink pair, but k different source sink pairs. Yeah, so we want to send 1 unit of flow from S1 to T1 and 1 unit from S2 to T2 and 1 unit from S3 to T3 and so on. We have our current capacity vector. Again, the resistances are as before. And then we have Q super I, which is an electrical flow of value 1 from SI to TI. And now we combine all these electrical flows. Oh, the dynamics is again as before, it's just that the meaning of this changes. Namely, the Q sub E is now a combination of the individual flows. And we either add all the absolute values or we form the 2 norm. Two norm meaning we take all the individual flows across the edge E, square them, sum them up, and take the square root. Notice for k equal to 1, these are the same thing. Yeah, because this is just absolute value, and this is if I square and take the square root, I again get the absolute value. So for k equal, so these are two possible generalizations of the situation for k equal to 1. Combining the different flows makes it worthwhile to share edges, and it avoids extremes, namely union of shortest path and Steiner tree. I will come back to this when I show you examples. And we asked ourselves which networks are formed by this dynamics. Does this dynamics converge, and if so, to what? So let me first show you, okay. So let me first show you some experimental results. All the experimental results are obtained by discretizing the dynamics and using Euler integration. So we now have a discrete set of values, a discrete sequence of values, and we say x sub b at time t plus 1 is x sub b times t plus a small step in the direction of the derivative. And this 2 should be here. Oh, how did I do this in LaTeX? Oh, okay. Anyway, so it should be. We typically in our experiments use a step size of 1/1000 and take random initial values and a large number of steps, maybe 10 to the 4 or 10 to the 5. The details of the experiments don't matter. So here's a first example, just to illustrate you that really the dynamics induces sharing. So this is the graph. We want to send 1 unit from node 0 to node 1 and 1 unit from node 4 to node 5. The edge lengths are shown as in the picture. So they are 1, 1, 1, 1, 10, 10, and the one in the middle has length L. So if L is less than 8, then the shortest paths are just going through the middle edge. But if L is larger than 8, the shortest connections do not use the middle edge. Yeah, the shortest connections are just the direct connections. So the observation we made for the dynamics, if L is less than 8.5, and I don't really know why 8.5, all flow is routed through the middle edge. So if you look at the picture down here, you should only look at the solid lines. What I show here is, this is for the bottom flow. This is the flow through the top edge. This is the flow through the bottom edge. And this is the flow through the middle edge. So if L is small, less than 8.5, there is no flow in the top and the bottom. And there is all the flow in the middle. Then starting at 8.5, the usage of the middle edge goes down. In the middle, and the usage of the top edge and the bottom edge goes up. And if L is larger than 10, only the top and the bottom edge are used, and the middle edge is not used anymore. So there is really a sharing effect. And also what is interesting, in the limit, the cost of the network and the dissipated energy are equal. So this dynamic sort of strikes a balance between what it costs to build the network and what it costs to operate the network. Yeah, because the C you can interpret at what it costs to build the network, and the E is sort of what it costs to operate the network, and these two things are equal in the limit. Let me show you a second example. So what we did here is we took from a grid graph for the Greater Tokyo region, grid graph in the sense that every node is connected to the 8 neighbors. And these edges have lengths 1 and square root of 2. And we took as the cities the 50 largest cities in the greater Tokyo region, and we required to send a flow of 1 between any 2 cities which are sort of whose distance is not more than the full distance, the maximal distance. And we started with the grid graph on the left, and the right side shows the state after 10 to the 5 iterations, and the thickness of the edges are the x values. And so it forms what I would say it's quite a nice network. Yeah? And here is a second example where we tried to mimic the experiment by Tero et al. This is a quarter of the region, the right lower quarter of the region of the previous slide, and we tried to use the cities which they used, and then on the right, again, you see the picture of the 10 to the 5 iterations. And I don't think after 10 to the 5 it has reached a stable state yet. There would be more edges which disappear. Okay, I come to the, so much for the experiments. Any questions at this point? Okay, then I go to the experiments. No, then I go to the analytical results. Well, the first result is that this dynamics really produces a solution for t from 0 to infinity. So it does not die out early. This is not too hard to see because, I mean, how can you die out early? You can either die out early because everything goes to 0, or you die out early because you explode and something goes to infinity. Well, nothing can go to 0 because even if, I mean, this is always a positive quantity. And even if it would not be there, yeah, it only diminishes like e to the minus t. Yeah? So things don't disappear early. And nothing can explode because this here is at most square root of k. Right? We have k flows and each one is at most 1. So it also cannot explode. So we have a solution for t from 0 to infinity. Then let me recall what the cost of a capacity was and the energy dissipation. So the cost of a capacity is vector is just you sum over all edges, the cost of the edge times the capacity of the edge. And the energy dissipation for a set of k demands is simply you sum up the energy dissipation of the individual demands. And this is just, potential difference between source and sink. And recall there is a global view and the local view. This is again the global view and the local view. Then the next result says if you look at the fixed points. So what are the fixed points? The fixed points are those points where all the derivatives are 0. So that means where the dynamic doesn't move anymore. And the first lemma recognizes the fixed points, namely that for fixed points, you either have that the x value of an edge is 0, or the x value of an edge is equal to the 2 norm of the flow vector. That follows immediately from the definition. Secondly, that for every fixed point you have, that cost of the network is equal to dissipated energy. This is a one-line proof. Let me go through the proof. So this is the dissipated energy, the global view. We rewrite it as the local view, where we sum over all edges and over all commodities, resistance times flow squared. We interchange the order of summation. We are in a fixed point. So this here is equal to this. And the resistance is C divided by X. So we get this. I've shown you this proof because I want to say that most of the proofs in the paper are very simple. I mean, most of the proofs are 2, 4, maybe 5 lines. Some. I will come to one which is more complex, but sort of I guess the difficulty was to find out what we want to prove and what we should prove, not actually proving it. Yeah. So the difficulty was sort of what is true, and okay, then here comes convergence. So when you try to prove convergence of a dynamical system, there is a method called Lyapunov. So Lyapunov was a Russian engineer of the early 20th century who studied dynamical system, and he said the way to prove convergence is you come up with a function which is non-negative and which as a function of time decreases. Then you know that the system cannot go in cycles, and it must converge to the set where the derivative of the function with respect to time is 0. So let me do this in more detail. So the Lyapunov function in our case is just the sum of the cost of the network plus the dissipated energy. And for technical reasons, we put the 1/2 in front. And this is a Lyapunov function for the dynamics. But by the way, all my results are what I say about the 2-norm dynamics. For the 1-norm, we cannot prove anything. And that means this L is non-negative. And if you look at L of x of t and you take the derivative with respect to time, this is less than or equal to 0 for all t. And moreover, for t going to infinity, x of t converges to the set where the derivative is 0, and this is the same as the fixed points. So this part is trivial almost, because I mean, you look at the L function, it has to go down. Now, because the L does never become negative, it has to become horizontal sort of in the limit. And that means if you look at the set of points where the derivative is 0, the dynamics has to converge to the set. Yeah, I think this is intuitively clear, and it's a standard theorem in the theory of dynamical system. This requires proof that the points where the derivative is 0 is equal to the fixed points. And moreover, if shortest paths are unique, then the dynamics converges to the unique minimizer of this function. If shortest paths are not unique, this minimizer might not be unique, and then it's more difficult to say against what the system converges. But if shortest paths are unique, the dynamic converges to the minimizer of the Lyapunov function. Yeah, this proof is also again not very difficult. What you do is you take the Lyapunov function and you compute all the partial derivatives. This is an exercise in calculus. It's easy to make mistakes there, but it's an exercise in calculus. I mean, because matrix functions behave slightly differently than standard functions. And then it's non-negative is clear because it's the sum of the cost plus the dissipated energy. So the only thing that requires proof is this here. And I cannot resist showing you the proof. So the way you compute the derivative is you take the gradient and you take the scalar product with the x dot. And recall that the x dot is this. And I can pull out the x sub e here by observing that the flow is just the q sub e is the x sub e times the potential difference divided by c. So this is this here. And now if you plug into this, then you get the sum over all edges. This comes from the scalar product. Then this here comes from here. And this here is the x dot. And now if you stare at this, there is an x, and there is a 1 minus something squared, and there is this something minus 1. So it's 1 minus a squared times a minus 1. And if a is positive, this is just an easy exercise in manipulating formulas. This is always positive. And you have equality only if either this is 0 for an e, or this is equal to 1. And then that implies that, yeah, the v is exactly the fixed points. This is the only proof I want to show. So I come almost to an end now. There are further properties of the minimizer, namely that this minimum of the Lyapunov function can also be written in two different ways. Namely, you can either say it is the solution to it's the flow which minimizes the sum over the two norms. And if you are confused now, there is a next slide where I interpret this for k equal to 1, and then some of these things will be familiar to you. So this is one thing. The other thing is that you maximize the sum over all the potential differences, subject to the constraint that on no edge the potential drop can be larger than the cost, the two norm of, again, the vector of potential drops. And then it also says that the optimizers of these three functions are closely connected. The proof uses the theory of convex optimization, in particular the KKD conditions for optimal solutions. And I will not go into the proof, but let me specialize for k equal to 1. And this is a busy slide now, but I hope you can still see it. So you're all familiar with two formulations of the shortest path problem. So one is I can formulate the shortest path problem in an undirected graph as a min-cost flow problem. I say I want a flow from the source to the sink. So a flow meaning there is an inflow of 1 at the source, an outflow of 1 at the sink, and I have flow conservation on everywhere. And I want to minimize the cost of the flow, which is just a sum over all edges. And of course, the optimum sends the flow across the shortest path. This here, you might also be familiar with. So here is a physical experiment which computes shortest path. So replace every node. Now we build a physical model of the graph, yeah, where we take the edges and we replace every edge by a string whose length is the cost of the edge. Now I take the source and I lift up the graph. Then the other nodes will fall down. The other nodes have a weight, yeah, so they fall down. How far do they fall down? Well, you cannot do more than sort of stretch these ropes to their maximal length. And so a vertex will fall down to its shortest path distance from the source, because then all the ropes on the shortest path will be tight. This is what this says. You want a potential function, and the potential function now is the height below the source, such that the potential difference between any two vertices, so is uv, is at most the cost of the edge, and you want to maximize the potential difference between source and sink. Yeah, so this is another way of formulating the shortest path problem. And I was familiar with this formulation and with this formulation, but I was not familiar that there is a third way of formulating the shortest path problem. Namely that you say, I'm searching for a positive vector, x, which minimizes C transpose x plus dissipated energy, where the P is computed by our formula from before. So LP is equal to B. And there are no other constraints now except that the X is in here also, right? It's the diagonal matrix here. So P is the potential function for the electrical flow with respect to the capacities X. And you minimize this, and this gives you the same solution. I won't go through the proof, but it's not very difficult. So this is a third way of characterizing the shortest path problem. And what I showed you on the previous slide is the generalization to K, so the multi-commodity flow problem. And as I said already, the proofs use the KKD conditions. Let me come to an end. I exhibited a dynamics that produces nice solutions. I've shown you the bow tie graph, and I've shown you the examples for the greater Tokyo region. And so these solutions look, at least to my eyes, they look nice. Also, the dynamics has nice theoretical properties. It converges. We can exactly say to what it converges. It converges to a minimizer of the Lyapunov function. And this minimizer can be characterized sort of as a generalization of the shortest path problem. On the downside, we do not claim any biological relevance. It's how we combine the individual flows to this Q is nice mathematically, but I don't think it can be argued that it had biological relevance. It would be interesting to find a dynamics that has biological relevance. I showed you experiments with the discretization. I used sort of the naive discretization and the naive way of integrating the differential, the discretization. This is very slow. I showed you the pictures for the greater Tokyo region, and one of them took 2 days on my notebook. Yeah, so I really started it on Friday evening, and it terminated Sunday evening. And so it ran for, it seems to ran forever. Nevertheless, there are faster methods of integrating such a differential equation, and we have to try this out. And sort of the last question from a computer science point of view is this an approach to efficient network design? I thank you for listening, and if you have any questions, I will attempt to answer them.
Thank you very much for the talk, Kurt. Thanks a lot. Are there some questions? So I've posted one question from UL. This is a general question. So he's asking 2 questions. So he asks, how do you see the role of theoretical computer science in your area of research? And are there some key conceptual or technical problems that theoretical computer science or mathematicians should try to tackle?
So I'll say that this question was mostly aimed for the biologists, so it's a bit redundant in terms of course.
Yeah, I'm not sure whether I'm the right person to answer this as a theoretical computer science, because I of course think we are the center of the world. No, but I find this. I shouldn't overstate it. Yeah, because this is the only question with a connection to biology on which I have worked in my life. I was intrigued, and I wanted to understand what's behind it. I think for the shortest path problem, we gave a good answer because the model was there. Is not our model. Yeah, we answered the model was introduced by biologists plus mathematical biologists, and we just answered the theoretical question about it. We analyzed the dynamics. Now for this problem, the situation is different because it's that we invented the dynamics. It's a natural generalization of the shortest path dynamics, but as I said, we are not claiming any biological relevance. So the others need to judge whether this has any value. For me personally, it has a large value because Vincenzo and I started discussing this 8 years ago, and it was sort of in the back of my mind for 8 years. I know I said I was sitting in trains and I was scribbling again on working on this. So now I've gained my freedom again.
There is one question from Corbin. Corbin, do you want to pose this question?
Thank you for the talk. It was very elegant. My question is just if you've looked at the case of dynamic food sources, so when the food source would change over time.
No.
Okay.
So if new food sources would come in, sorry, that's my phone.
Or even,
yeah,
or
so
even the simpler case of having two food sources and it just oscillates between them.
Okay. So this theoretical paper by Tero et al., where they introduced the model for the shortest path problem, they discuss this question at length because in the slime, the movement of the liquid or the movement is really a shuttle movement. It's a back and forth movement. So it's an oscillating movement. And they derive and they argue at length that it's fair to model this as a directed movement, as it is in an electrical flow. Yeah. So yes, they were familiar that, they argued at length that this is a fair formulation, a fair modeling. But there are other papers which investigate really what is sort of the meaning of these oscillations. Does the slime use these oscillations to not only to transport material through its body, but also to transport information? Because this, I said the slime does not have a nervous system. Nevertheless, it reacts. So for example, it tries to avoid light. And if you put part of the slime on the light, it starts to move away from the light. So there must be some kind of transport of information. And there are papers which connect this to the oscillations of the liquid transport.
Okay, thank you.
We have one question from Manish.
Yeah, this is more towards your open problems in the last page, really. I wonder what kind of parameters would you be optimizing for if you were using this shortest path approach to, for example, build an efficient network design or scan through many different possibilities of network design?
So what I find intriguing here is that the network that is constructed sort of strikes a balance between the cost of the network and the operating cost.
Right.
Because this is something we don't consider often in computer science. When we do network design, we either concentrate on the cost, but not on this mixture between cost and operating cost, which is very sensible.
Right. I wonder if you've given thought to, this, there's an intriguing notion I see. I'm not a computer scientist, but I see the discussion all the time of how our increasing use of computer technology and all of this setup that we have today, for example, is environmentally linked, because there are all these servers that are running. There is a cost because of that. and you think that that environmental cost could somehow be indirectly factored in to do efficient network design that has overall lower cost to the environment. Do you think the question could be phrased like that? Maybe it's too out there. I don't know.
Well, of course, environmental cost and dissipated energy are closely correlated.
Right.
Well, it's an ambitious goal.
Okay.
We have one question from Dashun.
Yeah. Thank you for the talk. It is really good. And so far, you're not claiming the biological relevance, but is there any reason that you choose this Physarum, the dynamic of this Physarum?
Because it's the only thing I know.
Okay. I mean, for the future big picture, like you will apply for other biological things, or?
Yeah, but somehow I don't know. This is I mean, it's all because I watched TV in 2012. and I was intrigued by the slime. It has no deeper reason.
Okay.
There's no deeper reason.
Thank you.
So I would have a question. So I would be interested, like, you presented this dynamics, yeah, and in some way, how does it handle faults or robustness? For example, if you change parameters, or if you insert noise or something, like, does it prevent? Do you know something about this robustness, or?
Okay, so first of all, it really designs networks.
Mm-hmm.
Yeah, so it's so there is a certain robustness against cutting edges. Yeah, because this is not just I mean, a Steiner tree would be singly connected. This is multiply connected. Yeah, so there is redundancy in that sense. And in the Tero et al. Paper, they sort of give some measures of robustness against edge failures. So this is one. Noise. So the way I wrote down the dynamics, the Q is the 2 norm of the individual vectors. Yeah, and I mean, so it in a certain sense you could say, I mean, I'm assuming here that the slime computes with infinite precision when it adds up the, or also here, I mean, the dynamics is Q minus X. Yeah, is there room for noise?
Mm-hmm.
There is room for noise in the certain sense that really the important thing is that the X dot and the Q sub E minus X sub E have the same sign.
Okay.
So you can put a 2 in front. I mean, you can put a constant in front, which is different for the different edges, which also depends on time. That doesn't make a difference. It still converges. The speed might be different, but it needs to have the same sign. And this is, of course, unsatisfactory, because you would still sort of require a very fine view near zero. I'm with Giovanna Morigi and Frederick Foltz. We are looking at the problem now where we want to add a noise term here on the right-hand side.
Oh. Mm-hmm.
And yeah, and then I mean the intuition should be, at least if for example the shortest path is much shorter than the second shortest, it should still converge. Maybe slower, maybe even faster, because the noise can bring you out of unfavorably situations. So yeah, we are investigating this experimentally. We are I mean, physicists know a lot about these things. I know very little, so they made me read a book on dynamical systems and noise in dynamical systems, and I think I'm now ready to talk to them. But no results yet.
Sounds very interesting. Very excited, yeah. Thank you, yeah.
Can I ask a follow-up question on that one?
Sure.
Is the noise term Gaussian? Do you have any
Yes.
sense of what? Yeah, okay.
I think most of the results of the physicists are about Gaussian. At least in the book, it's always Gaussian noise.
So I propose to ask follow-up questions, perhaps on Zulip. So we have a Zulip channel where this can be discussed to make sure we are on time for the next slot. Yeah? And thank you very much again to come here.
I enjoyed it. Thank you very much.
Thank you.